to continue on with our examination of periodic trends or patterns in the periodic table. The next one you will be familiar with from our element activity cards, but now we're going to be looking a little bit deeper about why we see the patterns that we do. So I'm talking about size here, the pattern of size. Now, just as a quick refresher, we already know that size of atoms increases as you go down a group, and we've said that this is because we're adding layers of electrons. There's a little bit more to the story than that. We're going to look at that today. We also know that the size decreases across a table from left to right, that it decreases as you go from left to right. Okay, so let's look at why we see those patterns. In order to understand the reason that our size changes, of the size of our atoms change, we need to understand electrostatic force. So let's write that down. Electrostatic force. Now, when we're looking at electrostatic force, there are two major kinds of electrostatic force. We have force that attracts and force that repels. So you may have heard before that like charges repel. What that means is that if we have, for example, two electrons that get close enough to each other, they will actually repel each other. There will be a force that pushes them away from each other. Or if you have two protons that are close enough to each other, you will have a force that also repels them. They are pushed away from each other. If you have opposite charges, they attract each other. So you have repel, you have attract, okay? And so if you have an electron, I'll just take this little electron right here. Oops. Let's see, it might have been easier to just draw one. It's too tiny, I can't pick it up. Okay, let me just draw one. So if I have a little electron and it gets close enough to a proton, they will actually attract each other. They will feel a force that pulls them toward each other. Okay, and so this is what we mean by opposite charges attract. Well, what does that mean for us in an atom? In an atom, let's put in an atom, the electrostatic force between the positively charged nucleus, I'm going to put positively charged nucleus. Why is a nucleus positively charged? Because it's full of protons, right? Remember that we have in an atom, we have our protons, which are positively charged in the nucleus. They also have some neutrons that are neutral, right? They have no charge. And then surrounding our atom in orbitals, and I'm just going to draw it now as a ring, as in our Bohr model, we have electrons, right? So when we're looking at electrostatic force in an atom, we're looking at the force between the positively charged nucleus and the negatively charged electron cloud. Now I have spoken about this electron cloud before, but we need to be very confident in what that means. Remember that when we're talking about orbitals and when we're talking about what electrons actually look like, we can think of it as a cloud around the nucleus, because what we know is that in an s orbital, we are most likely to find the electrons in a general sphere shape, but we do occasionally find that they will go outside of that general sphere shape, right? But they're much, much, much more likely to be in the sphere shape. So this would be like an electron. Let's do this. This would be like an electron cloud for an s orbital. We can also have electron clouds for our p orbitals. So for example, an electron cloud would look kind of like this for a p orbital. We'd have one lobe over here where you're very, very likely to find the electrons. And remember, these dots definitely do not all represent electrons. Absolutely not, right? There can only be 2 electrons per orbital, but it just shows where you are more likely to find it. So you're very, very likely to find it in that p orbital shape. But then there is the possibility that you find them further out. Okay, so this is our electron cloud, and the electron cloud, or the model of our electrons, is negatively charged. Okay, and our positively charged nucleus would be in the center. Somewhere in here would be our positively charged nucleus, right? Very, 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 very tiny in there. So the electrostatic force between the positively charged nucleus and the negatively charged electron cloud, whether it's a p or whether it's an s or a p orbital, that is the electrostatic force that matters for us. So the next question that you can say is like, well, what makes electrostatic force between protons, or I'm just going to put actually between our nucleus and electron cloud stronger or weaker? That's what we need to ask ourselves now, because that is going to give us our answer about how this force impacts the size of our atom. All right. So take a second, write this down. You may have to pause the video. I'm going to erase all of this so that we can start examining this question. This is our question. If we can figure this out, we can figure out why we see the size trends that we do in the periodic table. So first, when we're looking at electrostatic force, one thing we can know, or that we do know from electrostatic force, is that the electrostatic force, that's what this represents here. Let me write that. This is just our electrostatic force. And I'm going to write something here that's going to freak you out. Don't panic. Trust me on this. Don't panic. I'm going to explain it. Is proportional to, that's what that symbol means. So this symbol means is proportional to, and here comes some more symbols. Again, don't freak out, okay? Q is the charge, and I'm going to put Q of our protons or our positive charges multiplied by Q of our electrons or our negative charges. Okay? So hold on, nobody freak out yet. I'm still going to, let me just finish writing this down. So this is, I'm going to put the magnitude or the amount, magnitude of charges. So electrostatic force is proportional to magnitude of the charges. What does that mean? What does that mean? All it means is that as you increase the charge, which the way to increase the charge is to increase the number of protons and electrons, right? So as you increase charge, which means that you're increasing number of protons and electrons, that's how you increase the charge. The electrostatic force increases. The electrostatic force increases. Even more simply, as charge goes up, electrostatic force goes up. That's all it means. The opposite would be true too. If you have less charge, as charge goes down, electrostatic force also goes down. That's all this means, okay? Don't be afraid of seeing something expressed this way. You see how much easier it is for me to write this than to write all this explanation? Right now, you need the explanation because you're not familiar with this notation. Once you know what this means, this little fish symbol, you're going to be able to say, oh, great, I know that that means that if my charges increase, my force is also going to increase, right? That's why I'm getting you used to this, because it's way easier and faster to tell you this. Okay. So that explains a lot for us. Let's actually look at what that means. So let me write, this is the most important effect on size across a period on the periodic table. Okay, this is the most important effect on size across a period on the periodic table. Okay, so what I want you to know is that, let's look at it first and then we'll write it. So let's look at this here. As we go from left to right in a period, do you see that our number of electrons and protons is increasing, right? Our atomic number is going from 3, 4, 5, 6, 7, 8, 9, 10. That means, let me just draw an example. For example, going from, if we look at boron, let's do boron really quick. Boron has 5 protons, 1, 2, 3, 4, 5, right? And let's just put some neutrons in there. I don't even care how many. We're just looking at the charges. If I was going to draw a Bohr model of boron, I would then put 2 electrons in my first energy level, and then I would put 3 more in my second energy level. 1, 2, 3. Well, compare that to fluorine, for example, which has 9 protons. Let's do that. 1, 2, 3, 4, 5, 6, 7, 8, 9. Got a bunch of neutrons in there. I don't really care how many. A lot more protons than boron. And our electrons are 2 in the inner energy level, and then 7 in the outer. Can you all see that we have way more electrons and protons at play here than we do in this one? We have way more. Let me tell you something even more important. The most important impact is going to be looking at just the outer layer, because the inner layers are the same, right? If we look at the outer ring, we have 3 electrons in our valence electrons here, 7 valence electrons for fluorine, right? So this is boron, this is fluorine. And so it makes sense then that as we increase the charge, as we go from boron that has only 3 valence electrons to fluorine, which has not only a bunch more protons, but 7 valence electrons, that force, that electrostatic force that is pulling the electrons in toward the nucleus. Let me draw it in green. That force that is pulling the electrons in toward the nucleus is much greater because there's so much more charge, right? There's less pull. So boron electrons are sort of loosey-goosey. They're not being pulled as tightly into the nucleus, whereas fluorine is being pulled in really tight because it's got more charge. Okay? So let's see if I can sort of write that for us. So this is the most important effect on size across a period. And I'm just going to write, let me draw it in. Let me go back to the color black. As your number of protons and electrons increase from left to right, which we know they do, the size of the atom decreases from left to right. Why? Because the electrostatic force, or let me say this, the attractive force between the positive nucleus and negative electron cloud is stronger as you go to the right. Right? It pulls electrons tighter into nucleus. All right, it pulls the electrons tighter into the nucleus. So that's what you need to know about the size across a period, going from left to right. Going from left to right. If you were going to boil this all down, you would basically say that the reason that our size gets smaller as we go from left to right is because the attractive force between the electrons and the protons. Okay, I know this is a lot of words. Hopefully my explanations help, but you do want to be aware of and understand that the attractive force between the nucleus and the electrons is what has this effect on size. The more electrons we have, the tighter they get pulled into the nucleus, the smaller the atom gets. Okay, and so really this was a terrible picture that I drew because really this just needs to be bigger. Let me just do it so that we can see that boron is bigger than fluorine because fluorine electrons get pulled in tighter to the nucleus. Take a minute to write this down, make sure that you are clear on what the effect is here, and then we're going to look at one more effect. So let me erase all of this. And we're going to write another relationship between the electrostatic force and something else. So this time, I'm going to erase this. This time, we're not going to look at the charges. There's another thing that can impact how strong an electrostatic force is, and that is the distance between the forces. The distance between the forces can oops, hold on. Don't do that. Hold on, I've got this. There we go. The distance between the forces can impact our the strength of the electromagnetic force, or the distance between the charges, I should say, sorry. So the way we're going to write this is, think about this first. Okay, you can kind of think about it like a magnet, even though it's not a magnet, it's charges. But if you put a magnet really close to each other, does the force get stronger or weaker the closer you get? It gets stronger the closer you get. It gets weaker the farther you get. So that kind of makes sense. We're going to write this as it being something called inversely proportional, meaning we're going to write something, the 1 over something. So 1 over r squared. Now r is just our distance between charges. Okay, and now we say that the electrostatic force is inversely proportional. We say inversely proportional because it's a fraction with the other variable in the denominator. Okay, we'll get more into this later in the course. For now, you just know it says inversely proportional. What does that mean, that this is inversely proportional? All it means is as the distance between the nucleus and electron cloud increases, the electrostatic force decreases. So instead of them both increasing or both decreasing, if one increases, the other decreases. So again, let's look at it this way. Let's say as the distance increases, for example, let's say we have our nucleus over here and our electron cloud way over here. Actually, it's more like this. The attractive force decreases. Okay, so the electrostatic force decreases. If our distance decreased, meaning they got close together, if they got closer together, that force increases. Okay, and here, maybe I can even draw it like this. Our force pushing them into each other increases. We've got big arrows going in. They really want to go toward each other now. Okay, so your force increases. What does that mean for us? This is the most important effect on size going down a group. Why? Because as you add more and more layers of electrons, right, as you cannot fit any more electrons in there, the electrons just get farther from the nucleus. So as the number of electron shells or layers increase, the electrons are forced farther away from the nucleus, which means the attractive force, so attraction between protons, or let me just say the nucleus, the attraction between the nucleus and electron cloud decreases. Thus, atoms get bigger down a group. Atoms get bigger down a group. We know that already from looking at it. Now we know why. It's because as the electrons are forced to get further from the nucleus, those outer electrons are held more loosely. They're held more loosely, which means they're not pulled in as tightly to the nucleus. Okay? Once again, the point is, if you have a question on the test that says something like, why does the atom get bigger down a group? You need to say that it's because of the attractive force between the nucleus, the positively charged nucleus, and the negatively charged electron cloud. Okay, it's because of that force, and the force is decreasing as they get further from the nucleus. That's why. All right. So let's look at one more trend here, which is electronegativity. This is another new trend. Oh, by the way, I made a mistake here. This should have said 2. This is our second impact, or a second thing that we have to look at for force. So this last one is called electronegativity. This one is new, but we're actually going to be using the same things that we just learned about. So if we're looking at the trend of electronegativity, what is electronegativity? It is just the strength of attraction an atom has to pull electrons toward itself. So there are 3 factors that we have to know about. I'm just going to list them quickly here. So factors affecting electronegativity. Sorry about this. Let me try to write that a little bit neater. Factors affecting electronegativity, or how strongly an atom can attract an electron toward itself. 1, the number of electrons. Why? Because we know that it'll pull it more tightly toward itself if it has more electrons, right? How do we know that? Because what we just learned about electrostatic force. The force increases, so as the number of electrons goes up, the attractive force also goes up. Okay, so what does that mean? If we are looking at our chart here, our electronegativity is going to increase from left to right. Okay, so let's, just like our attractive force increases left to right, our electronegativity increases left to right. So let's write that. Electronegativity increases from left to right. Okay. The other factor, the second factor, is distance between the electrons and nucleus. Distance between electrons and nucleus. Why does this matter? Because the further the distance is, the less the attractive force, right? So let's write as the distance increases, the attraction will decrease. It will have less electronegativity. And so the impact of this is that electronegativity decreases from top to bottom. It decreases from top to bottom. So as the atoms get bigger, the electronegativity decreases because the atoms have less, the attractive force of the nucleus becomes less and less. It cannot pull those electrons in as tightly because the electrons just can't get close enough, right? They're too far away. But there's one more impact, and I want you to think about this for a second. Fluorine, let me write this too as well. Let's see. Let's say fluorine is the most electronegative element. But look at this here. Hopefully you have a question. Why is it fluorine and not helium or not neon? Maybe neon would be the most likely one. Neon has a ton of electrons, so it should have a really strong force. And it's really small, so the electrons can get really close. Why isn't it neon? Neon actually has very, very, very low electronegativity. It does not attract electrons toward it. Why is that? And that brings us to our third important factor. Our third factor is, does it even have space for another electron? Let's write that. Whether there is even space for another electron in its orbitals. Well, let's look at this. Let's look at neon. Neon's orbitals are totally filled up. It is a totally filled second energy level. An electron can't go in there. It doesn't fit, right? And so neon does not attract electrons in toward it. There is no space for another electron there. Whereas fluorine has this space right here, right? Fluorine has one space open for one more electron. And so that's why fluorine is the most electronegative element, not neon, right? And so let's just make sure that that's perfectly clear. So the group 18 elements, those are our noble gases. Our noble gases. Let's just look at those really quick. Which ones are group 18 elements? They're helium, neon, argon. If we can continue down, it's krypton, xenon, radon, etc. Those are our group 18 elements. Do not have space for another electron. They are highly stable, okay? So they do not attract electrons. They have very, very low electronegativity because they do not attract electrons toward them. Wait, that's not how you, electronegativity. They do not attract electrons toward themselves. Okay? So these, you need to know these trends. Electronegativity increases from left to right, decreases from top to bottom. Okay, let's look at this. So one way we can remember it is the smallest atoms have the highest electronegativity except for our 18th group. So if we let our 18th group go, we can know that the smallest and most highly charged, or not highly charged, but the ones with the most electrons and the most valence electrons and the smallest atoms have the highest electronegativity. So if we look at our valence electrons, fluorine is our absolute highest electronegative, and then it just goes down from there, sort of across the periodic table like that. Hold on, maybe I can draw it like this. Maybe I can draw it in blue. So fluorine has the, no, you can't see that. Yellow. Fluorine has the highest electronegativity, and then it goes down from there. All right? So those are the last trends that we're going to be looking at. Let's stop here for now.